Okay, so welcome to our presentation on the tea leaf paradox. Today we will explore this intriguing phenomenon and understand the fluid mechanics behind it. We will go through the equation that governs this phenomenon and the singularity generated by this phenomenon that highlights the limit of the model considered, and then we will talk about the application of this phenomenon. This is which is not so trivial. So, what is a tea leaf paradox? If you stir the contents of a cup containing the tea leaves, you may notice that the leaf migrates toward the center of the cup. And this may seem surprising. You might think that the leaves will be ejected toward the outer edges of the cup as a result of the centrifugal forces. But let me show you this phenomenon with a really simple experiment. So you just take a cup of tea. Can I play the video? No, it doesn't work. No. Oh yeah. Okay. So, do you see? Okay. The leaves migrate toward the center of the cup. So actually, there are other forces that explain why the leaves are not forced toward the edges in a as in a spiral centrifuge. This phenomenon was first explained in 1857 by James Thomson. The stirring makes the water spin in the cup, causing a centrifugal force outwards. However, it demonstrates that near the bottom of the cup, the water is slowed by friction. So this friction provides the centripetal force needed by the tea leaves to prevent them from moving toward the edges. And friction in the inside wall and the bottom of the cup creates a secondary flow, like you can see here, whose radial and axial velocity components are not tangential in the direction of the agitation. And that's why the leaves gather in the middle of the cup when you see it. So now I will let Paul explain the physics behind the tea leaves paradox.
Yeah. So now that you know a little bit more about what is the tea leaf paradox and how basically it works, I'm going to present what are the physics behind this tea leaf paradox, what are the fluid dynamics theories that can explain this paradox. So first, we call it the tea leaf paradox because it happens in a teacup, which is basically a cylinder with solid boundaries. And in this cylinder, we consider that the fluid flow is governed by the incompressible Euler equations that you see here. The cylinder is obviously axisymmetric, so there is no dependence on the fluid flow from theta, but it has swirl, so u theta is not null. We make the hypothesis in this case that the gravitational forces are negligible compared to the forces involved in the phenomenon, and that the viscosity forces are also negligible. So I'm going to explain a little bit more what happens in the teacup. So basically, a primary flow is induced by the movement of the teaspoon. So that's the primary flow you see here. And if we balance the efforts on the fluid in the teacup, we have the following equation where the pressure gradient force is equal to the centripetal force per unit mass. The interesting thing about the tea leaf paradox is that in the boundary layer, so in the walls of the cup, the liquid is going to be restrained by friction, and it's going to introduce a difference in velocities between the top and the bottom of the cup, which is going to bring a difference right here, and it's going to induce a new term in the force balance, which is going to result in an inward acceleration, so towards the center of the cup. So it's this acceleration that is going to cause a secondary flow to appear, and it's because of this secondary flow that the tea leaves in the experiment are pushed towards the center of the cup. So that's the tea leaf paradox.
Do you want to use the mouse and show you? Those people online can't see your hand.
Okay, I can.
No.
This is a laser pointer.
Okay. Sorry.
What's capital V and what's small letters V?
So capital V is the initial velocity, so it's the velocity that would happen if there was no friction, and V is the new velocity, the velocity that is a little bit less than big V because of friction. Okay, so this Tillich paradox may look simple at the beginning, but it highlights some very complicated and some very interesting special cases. For example, we have researchers that have used this problem by applying special initial conditions. So that's the condition you see here. So it's a very specific condition of stirring and special geometries. And they used these special configurations to create a layout with several symmetric secondary flows that you see here. And with the combined action of these flows, they've managed to create infinite vortices in the middle of the cylinder, so here in the critical ring, at a precise moment in time. So this is very interesting because it could be an evidence of a singularity in the 3D axisymmetric Euler equations. So why would it be so interesting? So what is a singularity? Basically, a singularity, it refers to a point or region in space or time where certain properties or quantities become infinite or undefined. So for example, the center of a black hole where the density is supposed to be infinite. So in fluid dynamics, it's often associated with infinite vortices core or shock waves. So it's very interesting because singularities often signal a breakdown in our current models and theories. So we might need to redefine how we see the fluid dynamics. So I specified a particular significance of the singularity in fluid dynamics. It's also interesting because it's major questions in fluid dynamics, and it has potential connections to many things, many concrete, many real-life applications. For example, the onset of turbulence in viscous flows. So that could be applied to piping systems, aircraft wings, so many things. So it's very interesting to notice. And basically, what you need to remember in the Tikka paradox is that the secondary flows are generated from a primary flow in a cylinder, and it could lead to possible singularities, which could question a lot about how we see the things in fluid dynamics nowadays.
So the Tillich paradox has many practical applications in fluid mechanics and engineering. It can be used to understand the behavior of particles in fluid flows, which is important in fields such as chemical engineering, environmental science, and geology. This phenomenon has been used to develop new techniques to separate red blood cells from plasma, to understand atmospheric pressure systems, and also in the process of brewing beer by wire pulling. This is a common method used to in commercial breweries to separate pellets and syrup from wort after the wort boil. I will explain in detail a little bit more about the separation of the red blood cells from plasma. So this system involves no moving parts. By applying a sufficiently high voltage on electrohydrodynamic airflow, an electrohydrodynamic airflow will generate interfacial shear and create a primary azimuthal circulation at the surface of the liquid. This vortex mechanism generates a secondary flow like the Tillich's paradox, which produces an inward radial force near the bottom of the chamber. And then the particles suspended in the liquid are then rapidly convected toward the bottom of the chamber. And this principle will enable to separate red blood cells from the plasma in a miniaturized device. So to conclude, we saw that the presence of two flows in the cup are governed by Euler equations and are explained by the centripetal force. The application of the Tillich paradox, can be applied to numerous systems in biology, in beer and whiskey brewing, in atmospheric systems, and the singularities challenge the theories of fluid mechanics. Okay, you can see the sources we used for this presentation. And any questions?
Audience questions?
If I understand correctly, like first we are assuming the flow to be potential flow, like without viscosity, and then at the boundary, are we considering like additionally after solving for potential flow, we are making that correction of boundary layer? Is it?
Sorry, I didn't understand the end of your question.
Yes. So what I'm trying to understand the solution of your governing equation. So first we are assuming it to be potential flow, that is with inviscid flow.
Yeah.
Basically we are neglecting viscosity.
Yeah.
And if we neglect viscosity, it's basically a rigid body. Like even at the wall, it will have maximum velocity.
Yeah, if we neglect the friction at the boundary layer, the tea leaves will stay on the walls of the cup.
Yes, yes. But ideally, at the wall, the fluid velocity should be 0. So then, because of boundary layer, and no slip boundary condition.
Yeah.
So, like after solving for potential inviscid flow, we are making that correction of boundary layer.
Yeah. That's exactly. Yeah. Yeah, and the difference in velocity between the top and the bottom, where the velocity is decreased, creates an inward acceleration. So it creates a secondary flow, and that is because the tea leaves are brought to the center of the.
So that minus small v square that you had in the correction term, that is due to boundary layer.
Yeah, that's the resulting term. Because of the boundary layer, this new term appears.
Go to the slide.
Yeah, sorry. Yeah, so that's this term that we, the boundary layer, the friction in the boundary layer creates this new term, and that's the term that will result in inward acceleration.
Thank you. It was very nice presentation.
Sorry, thanks.
Any other questions?
Yeah, the first equation is that's a force balance, right? That's
Yep.
Across the streamline. So Bernoulli equations along the streamline. If you go across streamlines, you have the pressure gradient balancing this centrifugal force. The fluid wants to keep on going.
Yeah.
The pressure keeps it. So it's low pressure in the center, high pressure on the outside. And that gives the top arrows, right? The black arrows.
Yeah.
And the next equation, you're just adding, you're subtracting that little v squared from both sides, right?
Wait, yeah.
It's the same equation, you're just subtracting it from both sides.
Like just to explain, like it's the equation doesn't change, but it's just to show the phenomenon. What is happening in the cup?
So the tea leaves are like buoyant; they're going to go out, but because the velocity is low on the lower on the bottom.
It modifies the pressure gradient, and so it creates an inward acceleration, and that's why they are coming back to the center.
Okay. How thick is a boundary layer?
So you have a velocity gradient top to bottom and side to middle, right?
Yeah.
Okay.
So the thickness, I really don't know the thickness of the boundary layer. I'm sorry.
We'll talk about it as the class goes on that thickness goes as square root of Reynolds number, and also, so basically because you have the lowest velocity in the center of the cup, so the boundary is basically going to increase as you go out. Other questions? Okay. Thank you. So they use this for beer? You said beer, they also want the sediments to go somewhere?
Yeah, they use this one. They start the big for the beer.
Oh, okay. And they drain out the sediment, I guess, right?
I guess.
Yeah, I think for boundary layers, that's going to be 6602. That's the next class. Next version of this class.
Great, so there's a harder version of this.
This is just the introduction.
I know. I'm just.
I don't know if it's harder. Right. Who's on next week? What are you guys going to talk about?
We're going to talk about, actually we have sent you an email that we're going to talk about motion of like biological species in the granular media.
Okay. That sounds fun. But this last group, Raphael and Paul, they did lots of images, graphics, and they kept it within the time. Segments. That's good. No one even looks at those side TVs. Does anyone actually look at those? Should I keep them on? Does anyone want them on? I just leave them. Okay. So remember, quiz 1 is Wednesday, 9:30. I've written the quiz. I try not to make the problems are not actually very long, just a few lines each. Please bring some scrap. Bring some scrap paper if you need it. All of you have practiced uploading your homework 1 to Gradescope, so you shouldn't have any issues with uploading the quiz. I would love to lecture actually after the quiz, but I found that people are like too brain dead and angry at me to want to listen. So we're just going to peace out. So when you're done with that quiz, you can just go be angry at me somewhere else. Yeah?
One, I think you said it wasn't OpenNote, and you'd be providing like certain like.
I'll write anything you need on the board. So basically, just bring the scrap paper and if. Oh, for my other class, I've been having people make a cheat sheet that you work on at home, but you can't. I think no cheat sheets. Just but if you have a cheat sheet and you want to bring it to the front and you want me to write something on the board, it'll be easier for me to write it. So I'll keep these up, and basically any equations people request, I'll write in the front.
Okay. And for the duration, like you just said that we just do the quiz and take off. Does that mean we have the full class period, an hour and 50 minutes to take the quiz?
If you really want, but I don't think it's going to take that long.
You'd be surprised.
Well, I think that some people just like to hang out, so that's fine. So I would give you a hint. Okay. So the quiz office. Okay. I started sending. I was trying to send people who got like 75% or less. If you got 75% or less on the homework, I'm going to send you an anonymous email. Well, it's not anonymous because you know who I am, but I try to hide that. You do want to try to Monday and Tuesday. You don't want to try to study for this thing. So I'll be get 75% or less. I'll be sending an email, but please come to office hours. So office hours today. I'll be in person 11 to 12:30, and there's an online one, but I can't do it at 4:30. I've got to go pick up my kid. Today's a special day, so I'm thinking 8 p.m., 7 or 8 p.m. Do people have a request? Who thinks 7 p.m. tonight? Who thinks 8 p.m. tonight? I see half a hand for 8 p.m. 8 p.m. online. Who would actually come to that? I saw half. Okay. All right. And Tuesday. What do people request? office hours. Let me see.
I have a question.
Yeah.
So on campus, you have Monday, Wednesday, 1 to 2. Is that still the time, or do we still have to check if you're gonna be in office?
It generally does work, but there's some. We have my postdoc advisor is actually coming to town and giving a talk.
So just double check before.
Yeah. I don't see anyone requesting. Does anyone want to have in-person office hours on Tuesday, or online? Yeah. What time?
11 to 12:30 would work.
All right, 11 to 12:30. Okay. And if you need any others, remember there's a class. Group me. Send me a message. Group me a time. But we're not going to talk about index notation much more after this quiz. So please, any like the home. Remember the solutions are homework solutions are uploaded. So especially the ones you got wrong, make sure you understand what's going on. And even the ones you got right, if you have questions about what you did, usually they can be pretty quickly explained. And the Q section. If you're listening to this online, the Q section quiz will be it'll be before midnight on that day. And if you have a conflict with that, you can just send me a note, and I can extend it for certain people. All right. So today I have a thesis. My students doing thesis proposal, and my postdoc advisors in town. Oh, let me give you a good talk. So today, 3:30 p.m., 3:30 to 4:30. There's a physics colloquium. Mike Shelley on he's from NYU and Flatiron, and he's going to talk about flows in cells. So it's interesting. So I worked at NYU after my PhD. And since then, he's worked for this place called Simons Foundation. Simons Foundation is a... Has anyone heard of Simons Foundation? Simons Foundation, Jim Simons, he was a mathematician. Basically, it's the world's most successful hedge fund. Jim Simons has $25 billion personally. Simons Foundation has $5 billion. You've never heard of it, but it has like twice the amount of money as this entire university. And this place called Flatiron, because it's a building, I guess they used to make like hair curlers or something like that. New York City has a place called Meatpacking District, one place called Flatiron. But he's basically, that foundation, they have like math and physics people. And that hedge fund, it's called Renaissance Hedge Fund. They only have 300 people. They've never had anyone quit. They managed to, basically being very quantitative and just using physics and math theories, they get 30% return on investments every year for the last 30 years or something like that. And they invested he has $25 billion, so he invested $5 billion into like pushing biology and computation in biology. So Mike Shelley, after he worked for Flatiron, he's never written another grant. He's doing pretty well. So if you want to work for them, go check that out and apply for Simons Foundation grant.
Where's that going to be?
Oh, this is going to be Marcus Nano. At 3:30. It's pretty rare physics colloquium has fluid mechanics, but this person has done fluid mechanics for his whole life. In fact, like a lot of he did the first papers of flapping flags, like basically why flags flap in the wind, why they don't just go steady, and he's applying those to basically organelles in cells, because there's also elastic filaments in cells that you have to take into consideration. Should be a pretty good talk. He's also a National Academy member. All right. Okay, so last time, let's just briefly, last time we talked a little bit about, we finished up talking about why tau has these two indices, lambda 1 and lambda 2, which we call k and mu. And we said that, hey, well, if you consider this one flow that basically has, and this is, people came in office hours to ask about this. This is a very weird flow that the farther you go out from the center, the higher velocity is. It's not very physical. But they call, the reason they like this is because of the directionality, that basically there's no, it basically comes from the center and goes outward. So this, they call this pure expansion. And if you have a negative sign, it's pure, no, dilation also means expansion. I guess pure compression. But in this case, it's basically everything's going out. And if you consider a flow like that, then as we showed last time, the tau becomes purely basically this k tells you the kind of like how much the stress changes as a function of this divergence, which occurs in the center. Like I think in this flow, everywhere divergence is 0 except for the center when it's not 0. Then we talked about what you need for your homework, which is conservation of energy. And with some manipulation, we wrote 2 forms of conservation of energy. One was basically conservation of mechanical energy, which we basically integrate Cauchy momentum equation, multiplied by U, and then we basically get the kinetic energy balanced like any kind of stress is done on the surface. For example, if you have a piston, you have a force and a velocity at the surface, you're going to get some work done by expansion, things like that, and also work done by body forces. If your object is like going in gravitational field, falling, it's going to increase in velocity, etc. And then the one that you need for your homework, is going to be this equation, because basically your bathtub water is going to be increasing in energy, right? Increasing in temperature. So you're going to use that the little e is going to be proportional CV times your temperature times your volume. That tells you how much energy you have in thermal energy. You're going to assume that there's no heat flux coming out of your bathtub because it's thermally insulated. And the energy that you're generating is actually coming from viscous dissipation. So basically, anytime you've got fluid that has gradients in velocity, so this gradient velocity means it's not just uniform velocity, right? Gradients in velocity. We showed that this viscous dissipation can be written as 2 terms, where the first term is 0 for any kind of Newtonian fluid. Okay, and the second term, if it's incompressible, you can write as 2 times viscosity of E double dotted with itself, where E is the rate of strain tensor. Okay, so, and for the homework, I suggested you basically, this E is has 9 components, but we're just going to be considered one-dimensional, kind of a bathtub where the velocity. At the top here, you're going to have the velocity U of your hand and the velocity 0 on the bottom. Very similar to that teacup problem that Raphael and Paul just presented. And that basically the size of your bathtub will give you the velocity gradient. I mean, their problem, their boundary layer actually set the gradient, but you're not going to have it. You're just going to assume the whole bathtub is actually kind of flowing, but it hit 0 at the end. So you're going to assume that basically your du dy is basically this capital U, which is the velocity of your hand, divided by L. Okay. So this phi will give you a dissipation per unit. Remember, these terms are all per unit volume. Per unit volume. So you have to multiply by the volume of your bathtub to get the right units. Okay. So this gives you the time rate of energy, and from that you can figure out how long you need to do that to get it up to the boiling temperature. Okay. All right. The last. So that's the last thing you need for your homework is a little bit on, the last question talks about hanging an oily rag. We have this nice class activity. Maybe quiz day might be a good day to do that, because I think some of you are going to finish early. All right. This is dangerous because I'm going to try to use technology here. Let me show you this. We'll do this. I'm going to dig up those materials. And we're going to do this Shumanagashi videos. All right. I have a little kit. I work with this. Sorry, we had to watch this ad for. I have this. I work with this art teacher, and we built these like 20 little kits that we can pass around. But basically, all this is. All right, we don't need to listen to this audio. Okay. Basically, what we're gonna do next time. We're gonna take water. It's just water, and then we're going to take this basically. I think they're kind of like they're like water-based paints. They're not oil-based, just water-based paints. But basically, water. Okay, there was a talk about this last week, but water has a lot of hydrogen bonds, and so water doesn't. To basically make new surface area water, you actually have to generate a lot of energy. It has got a high what's called surface tension, which we'll talk about today. And whenever you add contaminants to water, like pretty much anything you can think of, soap or paint, you add that, you're going to decrease the surface tension because you basically add little molecules that get in the way of the hydrogen bonds. So we're going to take these things, and you see, you just put one in, and you get stuff like this happening. So those are just different color paints, and it's just going outward because you get this. It's radially symmetric. And imagine it's like, physically what's going on is like you're taking a balloon, the water surface is like a balloon, and you're poking a hole in the balloon, and it's basically ripping outward. The whole balloon's under tension, and if you reduce the tension in the center, it gets pulled out. You can do cool things like, what did she blew, okay, so after she did this, she made this pattern, and then you can blow on it. I think she's just blowing on it, and the whole thing is like going like this. And then she's doing this. And I think if you're really, really careful, you can actually take this and make camouflage. Like this is before computer graphics, but they would basically, dip a whole machine gun through here and pull it out. Or like you want to make a scarf, like some of these clothing people are wearing, you can just pick up that fluid on top. And we're going to do this, if I can find the materials, you can just put a piece of paper on top, and then if you don't budget too much, you can actually pick up and take home what you put on the water surface. Do you guys want to do that? Yeah. Okay, so we'll do that. I'll bring it over on the, maybe we shouldn't do it on the quiz day. Because like mixing like fun stuff with not fun stuff. Okay, but I have the materials. I gotta collect them, but I promise you we'll do it. This is actually a perfect class. My other class is just too big. We can't do it. All right. What is? I can't see it there. All right. So we just saw, it's called Shumanagashi demo. Shumanagashi. I gotta make this up. Shumanagashi demo. We'll bring it on a fun day. All right. All right, so we have Navier-Stokes equations, but the funny thing is we've been here for 3 weeks, but we haven't solved like a single fluid mechanics problem yet. We've just been doing with the preliminaries. But actually, the homework you have right now, there's kind of fluid mechanics problems in there, but the next homework is going to be, actually, we're going to be integrating Navier-Stokes equations with boundary conditions and time dependencies. And that's why this is a graduate class, because of the time dependencies. All right, so Navier-Stokes. Okay. Now, you have 4 equations and 4 unknowns. The 4 equations, because that top equation is 3-dimensional, so x, y, and z are independent. And the 4 unknowns are basically pressure and velocity. And because velocity has 3 components, that's why it's 4 unknowns. So to solve, you need the boundary conditions. And I think you did this, you all did this, well, most of you did this in college. Solve, need the boundary conditions. All right. So we'll consider both fluid-solid and fluid-fluid interfaces. Civil engineers care a lot about fluid-fluid interfaces. There's a lot of civil engineering on the ocean, how where the temperature, where the energy from the air goes, how the ocean waves are created, how salt from the ocean actually gets in the air. Those are all deal with basically fluid-fluid interfaces. Salt, for example, one of the big reasons why we have so much salt in the air near an ocean is actually through the popping of bubbles. Basically, water drops go out and they basically pop, and those send this like explosions of very small drops. Yeah.
Are the salts still in their dissolved forms when they're in the air, or they like reassociate with like?
I think they just become like they're not with water anymore. They eventually those little once the drops get small enough, they just evaporate instantaneously. You just have basically floating like salt particles. But yeah, it smells salty because a lot of it's. I think this is a paradox at some point. People are like, why is the ocean so salty? Like if you make a bath of salt water, it doesn't smell like the ocean. It's because the waves are hitting and it sends up spray, and each of those sprays has little drops that basically break. All right, so we're going to talk about boundary conditions on velocity, and then we're going to talk about boundary conditions on the stress. So let's start with the ones that you're probably most familiar with. Okay. So there's something called a far-field condition. This is at infinity. So if it's like Raphael and Paul's Teapot experiment, if they're like spinning a cup, but the cup is the ocean, and they're just using your hand to spin it, if you're like miles and miles away, the velocity is going to be 0. So here we got velocity equals u infinity at r goes to infinity. And u infinity is generally considered to be 0. Okay, so that's called the far field condition. Field, because these are all like field theories of fluid mechanics where the pressure and velocity are defined at every point. All right, if any of you are going to study waves, these two conditions are going to be important. One's called the kinematic condition. Okay, so this condition says the normal current velocity is continuous, continuity of the surface. So if you imagine the fluid in the, so let's call this air and water. We have two different fluids. And here the velocities, some velocities, u hat. Kinematic condition says that u dot n so the velocity in the water phase, the normal component of the velocity in the water phase is equal to the normal component of the velocity in the air phase. So people that have formulated these have separated the conditions of the normal and tangential velocities. The tangential velocity is actually called the dynamic condition. So you might say, why do people bother splitting the kinematic and dynamic conditions? Like, why don't we just say the u in the air is equal to the u in water? There's these special cases called slip surfaces, riblets, and shark skin. But there's special conditions, like if you have so there used to be this paradox on sharks, why they could actually swim so quickly. Like if you ever see, like, watch these nature documentaries, like sharks are able to keep up with, like, really, really high speed boats, and they can turn really, really so quickly that, like, ordinary boats would just split in half. Partly their tails are really powerful, but the other part, which they've only studied there recently, is that they have skin that's composed of, they're called I think they're called denticles, which dent is similar to a tooth. They actually have a very similar structure to your teeth. They have these, like, little kind of like scale-like structures like this, denticles. And each one actually has a root, and they fall out and things like that. But what they've done some PIV on really close up with the shark skin, basically, each of these traps like a little vortex of fluid. And so as fluid streams by, it doesn't have the typical no-slip condition, which I'm going to introduce in a second, of basically being zero velocity, because the surface can have these secondary flows. I mean, you've heard secondary flows in several talks already, but this can actually reduce the friction of shark skin. And I think one of the things they've shown, and the riblets is basically, I think 3M made like a surface that has these little things. I think it can reduce drag like a couple %. But unfortunately, airplanes are just so large that it's not feasible to cover an airplane with basically these little things called riblets. I think McDonald's used to have a dish called riblets too, that was like processed meat in the shape of a rib. But it's not that one, it's the 3M one. Yeah?
Slip surfaces theory be in line with what they just say about how or why golf balls have dimples or whatnot, or is that a different phenomenon?
The golf ball thing is also covered in these little pores. So I would say they've understood golf balls a lot earlier than they've understood riblets. So the history of golf balls that originally, so I put this in I wrote a book on fluid mechanics and animal movement, but originally when the original golf players, this is in Ireland, Scotland, they basically played with basically mud balls, and then these balls started getting messed up. So they eventually chose to they have a tree that makes a special kind of sap that's pretty hard. And they found that the more they played with these balls, the farther they could actually hit the ball. And it's not because they were getting better at golf, but because these sap things started getting these divots in them, because you hit it and eventually it's going to get covered in holes. And what that does is delays the So a typical ball, basically, you're going to have basically this thing called separation. So separation in the back. And basically, these divots will change the separation point and reduce the drag on the ball. That's the basic idea why like certain kinds of like objects with a bunch of like pockmarks and things like that can actually have lower drag, even though they have higher surface area, because of the delay of the separation point. And so basically, you have P1 and P2 in the front and the back, and they'll be different because of the pockmarks. That's also a boundary layer problem too, because it has to do with the shedding of the boundary layers, which we really won't be able to get to here. And I'm not sure if they do that in 6602 either, but that would not be a bad course project. Okay, so that's why they have these two different dynamic and kinematic conditions, because there are ways you can sort of beat the dynamic condition with these secondary flows and things like that with slip surfaces. Okay, now we have fluid-solid boundary conditions. And we generally say if solid moves with velocity. So I'm going to try to introduce a new notation. We'll call this V. Then we'll say U is equal to V on the surface. And I think everyone who's taken fluids know this. They call this the no slip. Because you basically stick to the velocity. If you know the velocity of the surface, then you know the velocity of the fluid. All right. Okay. And if you don't have any of those special surfaces, we just say U is equal to U hat at the interface for fluid boundary conditions. Okay. All right. So notice these all these conditions we're dealing with velocity. So these are velocity boundary conditions, but there are also conditions about stress. And for the homework and to understand the Shimonagashi, you have to understand the stress conditions at the fluid interface. Oops, I cross everything out. And if you want to understand more, basically, spring 2025, not this year, there'll be 6607 interfacial fluid mechanics. Which is taught every a lot of these graduate classes, like this one, and I think instability is only taught every 2 years. And I teach that one. That will go more in depth in bubbles and things like that. Okay, so let's consider basically a little divot on the water surface, like imagine like a little rising bubble. So imagine this is the water surface here, and we're going to consider a little divot. So we're going to have the surface area S. Bound by closed contour C. So on the molecular scale, water has all these like little hydrogen bonds that basically want water molecules to stay near each other. And once you move water molecules to the surface, you lose its neighbors, and the water's not happy anymore. So you can think of water being like a trampoline. In other words, there's a force per unit length of magnitude sigma, and this is the surface tension, in the direction of the intercept face, in lambda direction. And I'm going to draw lambda carefully in a second. And the action is that water surfaces want to go back to its original configuration of being flat. So let's zoom in on that little part. We kind of have this, and let's say it's kind of like, oh, how do I do this? It's kind of like, it's basically like coming out of the, oh, that looks terrible. But it's basically like coming out of the page. Okay. C is basically this contour that goes around it, and S is the surface area. And there are 3 vectors I want to draw. So you imagine you're still in the plane. There's lambda, which is tangent to S, normal to C. All right, there's one coming out of the page. N, which is normal to C and S. And there's M, which is tangent to C. But it's like if I were to take, an orthogonal coordinate system and put it on the edge of the rising bubble, we're going to have these three vectors. So the interface, it's like basically we have an elastic balloon, and if you basically, poke out the balloon with your hand, there's a normal force that wants to push it back in. All right, the reason we have to be careful about these vectors is that there are 2 types of force. There's basically something called Marangoni force, which is due to, as you saw, the Shimonagashi, those rings went outward. Marangoni forces that are tangential to the surface, and there's normal forces that are perpendicular to the surface. So let's take that little area and do a side view of basically S. So let's say you have this, and let's say it was like this from the side view. We're going to take a little control volume around it. So that's C. And this is a control volume. And let's say this is of size S. And if you zoom in even further on this, and we'll call this a height epsilon. Okay, if you zoom in very further along that interface, and let's just kind of make it curved, we have basically N going out. So this is going to be the air side, and this is the water side. N hat going down, so that's negative N. And in the air side, you have the velocity U and T to be the T contains the information about the stress tensor. And in the water side, you have U hat and T hat. And because the velocities could be different in each phase, and they could have different viscosities, which tells you the stress, these have different symbols. All right, so let's take a force balance. F equals ma on that little, this sort of can-shaped object we have. Rho. So we got gravity in there, but usually, as we'll show, as the scale goes down, gravitational forces become less and less important. All right, then we'll use the same notation that we had last time when we derived Cauchy momentum equation. The force per area generated by the top side. So we'll call this air, which is the plus side, and water, which is the minus side. So this surface stress multiplied by the area. And then we have one more.
That need to be n hat,
Yeah, you're right. Thanks. Sigma lambda dO. This is the surface tension force. All right, so basically you got the stress from the top and the stress from the bottom and body forces. And from the fact that basically the edge of this control volume, there's basically tensions that are pulling this outward. We drew them on the previous page with this lambda, but basically they're tangential to the water surface. So these are in the direction, everything is a vector here. This is in the direction lambda. Sorry, I labeled them all epsilon. So that we're going to change this S to an epsilon. So it's basically like the control volume is epsilon tall and epsilon wide. So epsilon is the length scale of the control volume. And we'll return to this so we're going to non-dimensionalize Navier-Stokes equations to get the Reynolds and the Froude number. Those dimensionless groups naturally arise from consideration of different sizes of your systems. Then acceleration forces. So acceleration forces go as volume. So those acceleration body forces which scales as epsilon cubed. But surface forces, so the surface integral, the last two integrals, they go as epsilon squared. And so as epsilon goes to 0, this force balance just has two terms in it. So Cauchy, he said, remember he said all those surface forces are a function of how the interface is shaped. That's why we say T is a function of n. He also said, hey, let's contain all that information, the surface forces of that vector in this huge tensor, where basically to get the information out of the tensor in the appropriate direction, we dot it with n. So using this is equal to T of n, and similar notation for the phase below, for the air phase. And one more thing, we use Stokes' theorem. Okay. In the handout, there's this theorem that says you can take this line integral and you can write it as two terms. Basically, the gradient of how much that sigma changes, and this divergence of how much the normal changes. Okay. Then if you use all those together, we have the following. N dot t minus n hat dot. So I'm going to use, one more thing, using n hat is equal to negative n. Okay, so we're going to have the force per unit area on the plus side minus the force per unit area on the minus side, plus the gradient of the surface tension. So if you have SOAP, basically makes that this surface tension sigma. So sigma is the surface tension. It's a material property. Remember, this is force per length. And if you add little SOAP, basically it makes gradients in it, spatial gradients. It means that one part of the surface has high surface tension, another part that's low. I'm sorry, this is a minus sign. Minus plus sigma n difference of normal. I'm sorry, I keep on messing it up because I'm looking at the wrong thing. The next line, we're going to have it go. We're going to flip it to the other side. So that's equal to 0. And then because, our usual things, since these are arbitrary surfaces, since S is arbitrary, integrand goes to 0. And we have our final stress balance, which we're going to break into a normal and a tangential terms. So we're moving the stuff with sigma to the right-hand side. That's why the sign is changing. All right, let's explain what each of these are. So this is the force per area by the air side. So the difference in force per area by the top side and the bottom side. Minus sign. Well, if you take this 6607 class, this is how you figure out the shape of water menisci. Like if you look really close to the water surface, water tends to have this thing called a meniscus. It explains why small insects can walk on water, because they're kind of like, imagine you put you stand on a trampoline, the trampoline's going to deform. Well, basically that deformation amount, how much it deforms, tells you how much weight you're supporting. So this is the curvature. Okay, if you want to calculate, this is the two Gaussian curvatures, but you don't have to do that for this homework. Where R1, R2, they're called the principal radii curvature. This first n vector just tells you what direction that force is. And this is called Marangoni stress. Anytime you deal with surfactants, which is pretty much everywhere, you're going to generate tangential stresses. All right. So if you want to look at weight support, you want to look at the normal stress balance. And we basically take n dot of star, or this equation we'll call it star. So this is normal stress balance. So we already know the direction. So this becomes a scalar equation where every term here is just going to give us a constant here. So here, this is called the jump in normal stress. I'll illustrate that in a second when we talk about bubbles. And this is called the curvature force. Okay, so what does this mean physically? Let's consider a bubble at rest in a stationary fluid. So there's no velocities or anything. So the bubble's at rest, and the stationary fluid has no fluid motion, so all the velocities are 0. So here's what this looks like. We've got basically a pressure on the outside and a pressure on the inside. We'll label them P and P hat. So we'll call this a bubble. So we'll call this the air, and we'll call this water. Okay. We have the hat symbol here. So N hat goes towards your inner fluid. Regular N goes towards the water phase. And here we're going to consider the origin of the system to be here. So we're going to say this is equal to our radius vector. So for the whole course so far, we've dealt with Cartesian, and we do that for understanding. But if you do problems in cylindrical coordinates, your divergences and all kind of have funny depend on directions. So they have you kind of have to look them up to figure out the gradients and the divergences. So the stress tensor, remember in general there's 2 mu for Newtonian fluid. We have these parts, but if there's no fluid motion, clearly this part's 0, right? The stress inside is given by the hatted pressures, right? And remember, this is the identity matrix. And N is going to be equal to this is not the position vector. This is the radial vector in spherical cylindrical coordinates. I don't want to call it the position vector because to know a position, you got to have know what theta is too and z. So we'll call it the radial vector. All right. So physically, what does this say? The jump in normal stress. It means that if you're like let's say this is a really big bubble and you're an ant, and you're traveling from the inside of this bubble. Let's say this bubble all has the same pressure because it's just homogeneous. So there's no no velocity, so the pressure should be equal everywhere. But it says as you're an ant and you go from here to here, you're going to get a jump in normal stress. So there's going to be a jump in pressure. How much is that jump? Well, that jump is given by how much the radius is curved. So that's given by this curvature force. So del dot n, in this case, it's del dot the divergence of the radius vector. And because you're in cylindrical spherical coordinates, divergence is not that simple to write. It looks like this. And why don't you just work this out at your seats? what do people get for 1 over r squared times d by of r squared? 2 over r. Let's call this bubble with a radius capital R. So this radius 2 over r. All right, so let's combine everything together. The negative sign here makes us, we have p hat, so we have the air pressure minus the pressure outside. This is the bubble pressure minus the atmospheric pressure. In other words, there's a dump in pressure as you go from one interface to the other, and that's satisfied by that force balance. Physically, that means that small bubbles have high pressures. This has gotten a lot of attention from the alcoholic beverages industry. We have some French people here. Can you hear? Do you drink champagne? And you can hear the bubbles, right? If you put your ear really close, you can hear them. You can hear them popping, and you can feel them. But can you hear beer bubbles?
Not after I've had a few.
Maybe you might be hearing, but basically, champagne bubbles, I think, there's something to do with the surface. There's something to do with the chemical constituents that make champagne bubbles much, much smaller than beer bubbles, and so as a result, the pressure is much higher, and so you can hear champagne, but you cannot hear beer, unless you're as drunk as Don on a weekend night. So you can hear champagne, but not beer. But not beer. But so champagne has to be from that place in France called Champagne. Champagne. What is it? What do you call it if it's not from Champagne?
Sparkling wine or
Sparkling wine. Okay, and it tastes worse, huh? Well, it's definitely cheaper. Okay, so you can hear champagne but not beer. And there's a whole Physics Today article on how they how they figure out those bubble sizes. So this equation, P, the pressure drop is a function of surface tension R. You can also get this from dimensional analysis. With a system with P, R, and sigma, the only possible equation you can have relation between these two is with sigma over R. But that factor 2 can only be found from doing the calculus, considering this jump. So your homework problem actually uses the tangential stress balance. I tell you, my first time I taught the capillary class 10 years ago, I think we passed around champagne and took a picture and put it on Facebook, but that was a bad idea. Because the department chair got some letters from the parents. Why are you drinking on Georgia Tech campus with the class? So if anyone brings in any kind of beverages, there's going to be no pictures on social media from now on. Oops. All right, so for the homework, you're going to use this version. All right, this is the tangential stress balance. In particular, so basically, you imagine this is so side view of boat with the oily rag. All right, so this is there's probably a Mythbusters on this problem, but basically, if you are in the middle of a lake, generally, so this is a side view of your boat. So generally, you have sigma, sigma. So this would be clean water. Okay. But basically, if you've been hanging an oily rag, okay, this side, there's going to be oil rag. Here, it's going to leak oil, and this basically is sigma is going to be lowered by some amount, sigma minus delta sigma. And they said, and this is about sigma over 2. And this is generally true if you basically reduce surface tension, you can reduce sigma by a factor of 2 pretty easily. Just because the hydrogen bonds of water are so strong, and that's also the principle by which if you have like an oily pan and you add soap, you can basically reduce the surface tension and you can encapsulate stuff into the little oil things. So imagine you have basically the lower surface tension here than here. You're gonna have to draw some boat, I don't know, length L on all sides, and basically the force per length that propels you forward is going to be by sigma, in this case, sigma over 2 times L. Remember, sigma is a force per unit length, L is the width of your boat. This is the top view. That's what I just suggest you do. And that gives you the driving force, and the drag force, you can do something like, if you also consider it, so this is another side view of boat. You consider your boat to have like a height L2, then the drag force is going to scale as rho u squared times L squared. Well, this is called the dynamic pressure. Basically for a bluff body, valid for a bluff body. But basically there's going to be a higher pressure, fluid's going to go around your boat like this, and there's going to be higher pressure in front. That gives you the drag, and you're going to balance these two, the drag force and the surface tension force. Balanced by drag force. If you look in your literature, there's a coefficient called the drag coefficient. That's a functional Reynolds number, and I think for high Reynolds number, this function goes as constant, and for low Reynolds number, which your boat is not, f goes as 1 over Reynolds number. But you can use this relationship and do a scaling argument to figure out the speed of your boat. Sorry we went a few minutes over, started talking about champagne. Okay, I've taught you everything you need to know about the homework. It's going to be due next Friday. I'll answer any last questions on Monday and Wednesday, and I think we'll do the demo with the Shumagashi next week. And I will pass out homework 3, which is going to be about vorticity. So hunt me down if you need help with homework 1. I'm available. I'll try to make myself available today and most of tomorrow. So just send me a message, and I'll send a message to the group about a time that we all meet. Yeah.
With ultra forces and water walking insects like Microfilia.
Yeah. There's some insects that release some kind of, I'm not sure if it's waste products or some kind of soapy things. Yeah, for a small distance. Yeah, that's exactly what this is. There's also these things called camphor boats and soap boats that they've written papers that they can do it. I mean, basically you turn chemical energy into kinetic energy. You don't go very fast, but you do go.